Good day everyone, welcome to the third part of our video. In this case, we are going to solve a rigid frame structural problem. It's a two-dimensional structure. Now using the GRASP analysis and this GRASP software, given with these material properties, the loads, the load combinations, we have the section properties, the structure, the main structure, and we are going to determine the following. So these are the terms that we are going to determine, including this and all of this. So at the end of the video, we will be able to put an input to all of this required to be determined in our analysis of the structure. So let's proceed to our software. So this is our software. Before anything else, let us first set our unit into System International Unit because our problem is the SI unit. Okay? And then let us run a structure. I'm gonna add a material. Then let's add a material. The parameters that we are going to input here are the material properties from our given problem. These properties. So our modulus of elasticity is 21 kilonewton per square millimeter, so that is equal to 21,000 newton per square millimeter. So unit weight is 24 kilonewton per cubic meters, and our coefficient of thermal expansion is 12e negative 6. Then click OK, and then close. Set by default, and so we click the structure, and then let's run the structure wizard. I'm gonna save this. Let's say C. Prob C. Problem C. Problem C. Then click save, and then we're going to choose the regular base, regular story heights. Then click next. The number of base according to our given structure, that's 2. Number of stories, that's 2. Bay width, I'm gonna input 6 for much lesser adjustment on the structure later on. 5. There's typical story height. Click next. The material, that's concrete. This is actually 400 by 400. This is from the given. You see from here. Click next. Then this is 150. 150. Default material is concrete. And then click OK. And then see, as we can see from here, it by running the structure wizard, it will give us the direct structure, already a ready-made structure. I'm gonna remove these members from here, and then remove that node. Just perform remove unused node, since that will cause an error upon running the analysis later on. Then I'm gonna change this support from here. It's supposed to be a pin support, since it is what is being portrayed in our example or in our given. And then let us adjust the nodes to what they're supposed to be, the nodal coordinates. For here, this is supposed to be 9, since this is 5 and this is 4, that's supposed to be 9. Change. I'm going to change also here. Also here, this is supposed to be 10. This is plus 4, this is 10. And same here. And then that's it. Now we're going to check if our dimensions are correct. It's 4 meters, 5 meters, 6 meters, and 1 meter. I'm gonna remove them in order for it not to settle during our analysis and the development of our analysis. And so let me view, I want to view, actually want to view the member numbers and the node numbers. At this point, let me check if the materials are correct. No, we can see it's not correct, so I'm gonna set it again. And structure, then materials, then concrete. Add material in concrete. And so it's 21,000. This is at 24. This 12e and -6. Then click OK and then close. Confirm. And I'm gonna check country. Can be highlighted though to apply uniform na concrete. And set the material into concrete. Because basically it will really give an impact, a big impact, a big difference. So the material properties that is used in different structures, the results, analysis results will be really different. So let's make sure that the materials used in our structure, even in particularly the analysis, is correct. It's the exact to what is given. So that's it. So let's move on to adding or defining our loads. So we go first with the dead load. Then I'm gonna select a horizontal because the dead loads and the live loads. The dead loads and the live loads are actually going to be applied in all the beams. So applied in all beams. So as stated in our problem. So let's go apply all the dead load and the live load in the beams. So I'm gonna select the member and I'm gonna highlight this and then add a load. And then I'm gonna add this 31. That's our given load for the dead load. And click OK. Now okay, then let's proceed with adding the live load. That is 10 kilonewton. Sorry, 10 kilonewton meters per meters. I'm gonna add this and this. Sorry, add and this. Then click OK, and so we have our live load. So let me go back to showing all the numbers, columns, and the beams. Then let me proceed with adding the live load. So there's no live load in our load case here, so I'm gonna add the load case, new load case that is the wind load. So wind load is still a basic load case. I'm gonna add wind load. And click OK. So we have proceeded to our wind load application. So I'm gonna apply a wind load. I'm gonna apply this. Our given problem structure, there is this point A, which corresponds to the node 7. That's 40 kilonewton. Okay, and then point C, that is that corresponds to node 2, that is 20 kilonewton. Okay, then we have applied our wind loads. Next is we're going to make our load cases. We're going to define our load cases. The load combinations. We have the load combination. There are two cases. For case number 1, so I'm gonna add these two cases. And since they're not yet here, so I'm gonna make them. I'm gonna add them. Add load case. That is, I'm gonna name case number 1, and it's a combination type of load case. Okay. And then again add the second, the case number 2, then still a combination load case. And then let's edit or change. I'm gonna save this, give us the problem C. This then I'm gonna change loading. It's supposed to be one point 1.05 this is 1.05 and 1.7 sorry, and here this is 1.05 1.05. This is 1.275, 1.2 and 1.2, 1.275. Click OK. So here we have already defined our load cases. Case number 1, case number 2. Now let's move on to, so since we already have applied the load, the basic loads and load combinations, now let's go and try to run the analysis and then answer this, determine this reactions and etc. Okay, so I'm gonna make sure that this structure will be analyzed as structure as a frame, and then I'm gonna again remove the unused nodes and then run the analysis. Dead load. So, now let's move on to determining the reactions. These are reactions. So here first we are tasked to determine the reaction of the support F. So our support F corresponds to our support at node 1. So here we can see the results. So let's input the results here. So our results, the vertical force, the force along y axis of 182.05 kilonewton. It's 182.05 kilonewton, and so the units I'm not gonna put it again for redundancy. While for the horizontal force, that is along the x-axis, it's 7.07. This is 7.07. And then the moment along that node or point F, that's node 1, that's 9.94 kilonewton meter. This is 9.94 kilonewton meter. Okay, now I'm gonna save this, and let's proceed with the next things that we are going to determine. So at this point, let us determine the end moments of beam CD due to the combination load case 1. So I'm gonna change this to the load case 1, so it requires us to determine so. Then at member CD, so the member CD is this. And member CD is this corresponds to the node 2,4, which is actually a member 4 in our structure. So since we are talking about the moment, moments, the end moments. So I'm gonna show the analysis or show the bending moment diagram. So this is the moment for our case 1. Talking about the case 1. So the end moments, talking about the end moments, so we're gonna get the moment at C and at D. So I'm just gonna click this member here to show us the exact moments at ends at both ends, the C and D. So, at the end of C, this is end of C is actually at 0 x meter. No, the meters is from 0 meters. It's because it's at C, at point C, at node 2 or at node C, it is where the span starts. So it is at 0. So the moment there is actually negative 136.878. So I'm gonna input it here. Negative 136.878. 878. Then at D, so basically point this is the end moment here. So I'm gonna move to the end span. So at 6 meters, so this is negative 165.604. So this is the end moment at D. I'm gonna input it there. Negative 165. 165.604 kilonewton meters. So great, we have determined the end moments of the beam CD due to the combination load case 1. Let's check if it's not combination load case 1 and it's okay. Now let's move on to the next that we have to determine, that is the end moments of the beam CD due to the load case 2. It's just the same member, or you have member that's in our structure. It's a member for node 2 to 4, but on a different combination load case. So it's a load combination number 2. So I'm gonna check case 2. Still we are at our moment diagram. You can pick this member and determine the end moments. So the same manner, so our end moment at C, that is at 0 meters, that's negative 58.766 kilonewton meters. So I'm gonna input it here. Negative 56.766. And then at D, the end span, 6 meters, that's negative 213.285. And 213.285. Let's check if this is okay. 213.285. Correct? That's correct. And so let's proceed with the determination of the actual force in column CF for the different load cases. So there are specified load cases here at determining the actual force at column CF. So our column CF is here. So this is the corresponding member is member 1, that is from node 1 to 2, column CF. So let's proceed with showing our actual force diagram. The actual force, and we are tasked to determine the actual force with the load case of wind load only. Let's go first with the wind load. I'm gonna change load case to wind load, and so it shows us the actual force diagram. So basically, the actual force here is 20. That is 20 kilonewton, but we can make sure that this actually is by showing, by looking at our detailed member detailed forces for this member. So I was wrong. I actually read this report. I'm gonna view the result values. to give us the result value. So these are the result values. I'm gonna tap it here, remember, so it will give us the exact result. That is, this is the actual force. So it's 31.351 with a wind load case. So I'm gonna input it there. This is 31.351. Yes, and it's okay. And then let us change the load case to what is being demanded. So I'm gonna put this and change it to the dead load only. And let's proceed to the dead load, and so it will show us the actual negative 182.1. But to make sure and to have the exact, it's 182.052. So I'm gonna use this as an input as our answer. So the actual force at CF, column CF, is negative 182.052. 182.052. And then for the load case, there is a load case combination load case 2. That's case number 2. So this is our actual force at this column CF, or number 1 in our structure, in our structure. The actual force at that column CF, column 1 is negative 275.311. I'm gonna input it there. 275.311 kilonewton. Now let's proceed with determining the maximum left end moment for beam CD. No, the beam CD. Our beam CD is actually this, still at member 4. The connection from 2 to 4, node 2 is member 4. And so we are tasked to determine the end moments. The maximum left end moment for CD. So maximum left end, so we're talking about the maximum left end. So the left end is at C. So we're going to determine the maximum moment at C, and at which load case will it occur. It occurs. Did it occur? Because it actually already occurs from our analysis. So, left end moment. Let's go to our moment diagram. So moment diagram. Take note that the maximum moment is only the positive. So this, I'm gonna show this. Let us evaluate it first from the dead load. The left end moment from here. This is the left end moment. We're gonna start at 0. So left end moment, that is 0. There's negative 81.962. Negative 81. Then for the live load, that's negative 26. Much bigger. Load case 1, that is negative 136. And the load case 2, that is negative 558.66. So here we can see that our maximum negative moment is actually, and the right end is actually at load case 1, that is negative 136.876. As if we're going to compare from the other load cases, the wind load is far greater. The wind load positive moment is 52, but I regard that we have a negative moment, a positive moment, which is 52 value. So the wind load, then the dead load, So 26, while for the dead load we have 81. So therefore, from the load case number 1, our maximum end moments, end moment for number CD is the negative moment, that is 136.178. 136.878 at load case number 1. So negative 136.878 load case number 1. Case number 1. Excuse. Now let's proceed with determining the maximum right end shear for member AB. Note that our AB is this. From our structure, the corresponding nodes are 7 and 8, and that's member 8. So we're talking about determining the shear, right end shear. So the right end is actually at B. So we're going to determine the maximum shear at B. So at B, I'm gonna show us the shear diagram. I'm gonna click this, the maximum right end moment shear at B, and then at what load case will it occur? Same manner. So let's stop. The shear at this member is 153. And so I'm gonna talk about we will look at the span, the end span, that is 6 meters. So that's basically 157.053 for the load case number 1. Let's check for the dead load. .94 much for the load case 1 is much greater, but for the live load 30, so this one's still greater. About the case number 1 load, case number 1, yes, that was 157, negative 157.053, and for case 2 that is negative 162.8. So that's a lot bigger. Regardless our maximum shear, the right end number, the beam AB, number 8. So that is negative 162.769, negative 162.769 load case 2. It's actually a course of load case 2. Case number 2. I'm just curious, I just want to test how about the self-load. It will be the moment, maximum moment at this end. So 6 meters, so it's kind of small. How about the ultimate load? Oh, it's actually 192. But here I'm assuming that what is the questions that want us to determine are the given load case, that where the problem is actually giving us dead load, live loads, wind loads, and the load cases that are being implied. The load case 1, case number 1, case number 2. I'm not going to include this in the evaluation of the maximum shear at a right end of numbers AB, or the beam AB. I hope that's clear. So okay. So let's proceed with determining the displacements at joint B due to the wind load. So I'm gonna change this to wind load, and our joint B is actually corresponds to our joint 8, no? Joint 8 is the second story. Joint 8, so I'm gonna show us the displacement in the form shape, and here it will show us the displacement on X, Y, and the rotation. So let us input our values, the required values from the structural analysis. The horizontal is 25.168. 25.168. While for the vertical, we have negative 2.9 E to the negative 0.2. The negative 2.9 E negative 0.2, if I'm not mistaken. Let's check it again, double check, yeah. And for the rotation, we have negative 2.5 E, negative 2.5 E, negative 0.2, exponent of negative 0.2. And so we have obtained the displacements due to the wind load. Let's check it if it's on a wind load case. Okay, so last but not the least, we're going to determine the maximum span moment for member CD. So again, our member CD is this, our member 4 in our structure at the grasp. And so the maximum span moment for member CD due to load case 2, so I'm going to set the load case into piece number 2. Then let's show the moment diagram on the maximum moment. I'm going to evaluate this. I'm going to place it. So the maximum moment is when the positive and the negative shear will meet. So let's get 0. So I'm just going to evaluate it using a judgment. So here we can see that 2.750 to negative 11.502. So here we can say that the maximum moment is at 84.648 kilonewton meter at this member, this CD member, the beam CD, the member 4 at our structure in the grasp. So I'm gonna input it there, 84.648. And then we're done. So actually, these are not the only values that can be required given with the different problems that we're going to use or to analyze using the grasp. So it is always upon the end user to define and to determine which kind of reactions, the displacements, the moments, the shear, the axial forces, and etc. to determine using this analysis. It's a very convenient tool. So I'm gonna edit this, and so we're done. Thank you for watching this video. I hope you learned something. Have a good day. Thank you.